I wanted to start off by thanking Marty for inviting me. It has been a lot of fun so far, and I'm looking forward to all the rest of it. So thank you. What I'm going to talk about today, and well, maybe I should start a little differently. I'm really pleased that I got to talk twice, that I get to talk now and I get to talk again on Saturday at 4 o'clock. Because the challenge I had today wasn't what it was I could tell you. It's what it is I couldn't tell you. That's because when you have a theory of everything, that's very big. It's very tall and it's very broad. And to actually describe how things work just can't be done in an hour or even 2. And typically the material I'm going to go over today, I take about 8 or 9 hours to do. So I'm going to take all of that and squeeze it into a very short amount of time. The problem with that is it makes it very hard to understand. If you go real quickly, I can't take the time to derive things, so I'm pretty much going to have to resort to just making statements. If you want the logic and the derivations, then you'll need to find it in the books, which are free on Google Books, or on the YouTube, the web. I've got a lot of videos out there. Those are some of the places you can find out more information. If anything I happen to say interests you and you want to find out more about it, that's the YouTube and my website, and the MBT Events is a website that organizes all my speaking events, so they'll let you know where I'm going to be when and that kind of thing, where I'm talking. I approached this work a lot differently than the people you've heard talking here today. Well, I shouldn't say that. I've approached some of it in the same way, but what I'm going to talk about today is very different. And that's because Marty and Lynn and Jeffrey have come to the conclusions and the understanding that they've come to based on experiment, based on their experience. It's experiential stuff. Actually, it's good science. It's experimental science. But you've noticed there's very little theory in it. Matter of fact, there's a whole lot of things that have somehows in front of them. Well, we start with these microtubules and these quantum mechanics things, and somehow we get a consciousness, you see. Or when we are in our office building and we have to go clean up the mess that we made, you know, we go clean it up, and somehow that changes our health. That changes our attitudes. So there are a lot of somehows. And I got started down this path. I was a physicist just getting out of graduate school. And my path in physics, which was my first job, which happened to be in Army Technical Intelligence. You know, ooh, that intelligence thing again, right? There's a reason for that as well. But I very shortly, probably within 6 months of taking my first job, I met Bob Monroe. Bob Monroe, this was 1971, okay, 71. So there was no TMI, there was no Monroe Institute. Bob lived at a farm called Whistlefield. And at this farm, he had just built a laboratory for the study of consciousness. Bob Monroe knew his experiences in the outer body were real, and if they're real, then they ought to be measurable. They ought to be science. There ought to be a way to study them. They ought to be reproducible. It wasn't just him. So he built this lab, and that's about when I ran into him, myself and another person that worked with me who was an electrical engineer. And we made a deal with Bob. We said, Bob, you teach us what you know so we can experience it, because if we can't experience it, it's not ours. And we'll run your lab for you. So that deal was cut, and after that, Dennis and I spent maybe 20 hours a week with Bob Monroe at the lab. In about a year or so into that, Bob taught us how to go out of body on demand whenever we wanted to. And we became the first of what he called the explorers. And you can still find those old tapes out on the internet someplace. If you go to TMI, I think they might have them. So that's where I started in about 1971. And maybe I started just a little before that. As a graduate student, I took Transcendental Meditation and found out that I could debug computer code in my mind much faster than I can debug it if I was looking at the computer code, looking at the printout. I just bring it up in my mind, it would scroll by, and all the lines, all the statements in the computer code that were not right, had errors in them, were red. And I just look at the red ones and say, oh, okay, I remember it because I wrote all the code, so I know exactly which ones were which. I'd go back in my 4 boxes, which was about 6,000 cards. That's in the bad old days of punch cards. And I'd find that line, pull out the card, make a new one, fix the error, and put it back. In those days, debugging was not an easy thing. There was no debugging software. You just looked at each line and tried to find out where the error was. And in those days, the error may not have been anything you did. It may have been something the key punch did. So it was a lot harder. So when I got an opportunity to meet Bob, I already knew that reality was larger than the physical reality. So I'm early 20s at this point, early to mid 20s. Well, my point going out to Monroe Laboratory was I'm a physicist. What physicists do is understand how reality works. That's our job. We model reality. That's what I wanted to do. I wanted to know how could I do that debugging of my programs? How did that work? And what else did I do? And what were the limits? And why did it work that way? Why wasn't it some other way? So I spent the next 35 years trying to answer those questions. The first 5 of those 35 were, like I said, 20 hours a week with Bob Monroe in the lab doing experiments. Now, we did remote viewing, and we did healing, and we went out and had conversations and made friends with non-physical entities, and we did all that, everything that we could that was evidential. But that was really before remote viewing was a thing. It's before remote viewing even had protocols. It was just kind of almost ready to happen, but hadn't quite happened yet in 1971. So in, a few years later, was it 76 or so, when Putoff and Targ published their results in IEEE, peer-reviewed IEEE, a solid science journal. We were thrilled because that was the first big breakthrough into traditional science and engineering. But we had already been, I guess, about 3 or 4 years into our work with Bob at that time. So what I'm going to present to you is the results of that 35 years worth of trying to figure it out. Now, I never could have figured out what I did or come to the model that I did by thinking about it. I could only do it by doing experiments in non-physical reality. But when you can go out of body whenever you want, then it's easy to repeat your experiment precisely. You can change variables, do it again, see what difference it makes, change variables, try things different ways, and eventually you can do good experimental science in the non-physical world to see how's it work, what are the limits, how far can you get, what can't you do, and if there's things you can't do, why not? You see? Well, that's what I wanted to do, and I finally came up with, and it's probably I started in about the middle 1990s and finished the books in the early 2000s with a logical model, and I like to emphasize that word model. This is a model, okay? And don't confuse a model of reality with reality. They're two different things. This is a model of reality. In science, we often call models theories. And when I first wrote it, I was writing a theory of consciousness because I knew that consciousness was fundamental. And if you understood consciousness, the rest of it was going to fall out of that. So in 2002, I published my big tale, 3 books. And what I had accomplished was a model that started at the earliest point that I could start, which was primordial consciousness, just the basic, most bare elements of what consciousness is. Okay, something that could choose between A and B, period, nothing else. Okay, just like biologists, when they talk about evolution of this on this planet, they start with that first cell. Now, if you give them a cell, they can evolve. All the trees and the plants and the people and the critters can all evolve out of that. That's our evolutionary biology. Well, I started with this consciousness cell. So that's number one assumption I made is consciousness exists. Not a tough assumption. It's pretty self-evident for most people. Consciousness exists. But it existed in a very primitive form. And after that, my second assumption was evolution exists. If you've got a system that can change, then it will change in order to better survive, more easily work with its environment and so on. So those are my only 2 assumptions. From those 2 assumptions, everything else is deductive logic. When you start with that, you can say, okay, given this cell of consciousness, what would have to happen next? What's it like? So what are its properties? And what would be the next step that is logically necessary? And you take that step. And then what's the next step that's logically necessary? And you take that step. And so on it goes until you're all the way to the end of the line, and you've got a whole theory of consciousness. But it's a logical theory. There aren't any, and somehow, you end up with this. All of it is logical deduction. After I published this theory of consciousness, with a little bit of physics in it to show that consciousness was fundamental, about 2 years into it, so I published in 2002, this would have been like 2004, I got a epiphany, kind of something went off in my head, and I realized that the same principles, the same ideas that were at the core of my model of consciousness also solved physics problems, that it was good physics. And I said, you take these same ideas, and I can explain now things that physicists don't know. Like, why is the speed of light a constant? So it comes out just logical deduction, why that has to be that way. Not some justification of why it is, but why it has to be that way. Well, that means that's relativity. All of special relativity is built on that one concept. The speed of light is a constant. Once you know that, a little bit of algebra takes you through special relativity with weird things like time dilation, length contraction, mass grows as functions of speed. So all of that physics then falls right out. And physicists don't have any idea why C should be a constant. So yeah, that's the only thing we know of in this reality that works that way. Everything else, velocities add. If you're in a car going 10 miles an hour and you put your hand out the window with a baseball and throw it in the forward direction of the car at 10 miles an hour, and the baseball's going 20 miles an hour relative to the ground, velocities add. Makes sense. Speed of light doesn't work that way. It's always a constant. Doesn't matter what its source is doing. It's always a constant. Okay, so that's a big unknown. It's a big paradox, why that should be that way. And then I realized this one first, that I could explain quantum mechanics. quantum mechanics is a science that really got started around one seminal experiment, and that was a double slit experiment. That double slit experiment had a result that was just very puzzling. The result was that if you send single particles one at a time at two holes in a background, you expect they'll pile up behind each of the holes. That's what particles ought to do. But what they found out is they would distribute themselves on the screen behind the holes in a diffraction pattern. And we'll see one of those a little bit later in the slides. They distribute themselves all over the screen. And they see you shouldn't do that. Particles should travel in a straight line until they run into something. That's what Newton told us. Well, these not only didn't go in a straight line, but they arranged themselves in a very specific pattern. You see? So that was a problem. And the same ideas about consciousness explained why that happened. And again, not only justified that happening, but explained that it couldn't happen any other way. This is the way it had to be. And just recently, I've taken that farther and have some experiments now out now. Just 2 days ago, this set of experiments that I've come up with, quantum mechanics experiments, have been put into a peer-reviewed physics paper. Yay! So now there's something out there in the language of the people who can actually do the experiments. Another fortunate thing is the experiments aren't that hard to do, and they're not that expensive. So I think they will be done. And what they will do is if they work as I hope, they will clearly say that this reality that we live in is a virtual reality. It's an information-based reality. And I have yet another experiment that I haven't written up yet that will say, with no other possible explanation other than consciousness is the computer in its virtual reality. So those will be very big things when they get going. So that's in the works, and hopefully over the next year we'll get those experiments done, or the next couple of years anyway. These things are slow. So that's kind of where we are with this. And I found out in writing up those experiments that from a virtual reality perspective, I could rewrite quantum mechanics into a science that was not weird. Quantum mechanics is known as weird science. It does weird things like particles arrange themselves when they really, no reason why they should do that. But there's a lot of other anomalies in quantum mechanics too. And the reason it's so weird is because people are looking at it from the wrong perspective. When you look at it from the right perspective of virtual reality, all the weirdness goes away. And you can understand logically what the results are going to be. There's a famous quote from Richard Feynman, shut up and calculate. And that was said to his students who said, Dr. Feynman, what's going on here? Why does this work? Explain to me how this quantum physics works. And Feynman said, shut up and calculate, because that's all he knew how to do. And that's all any quantum theorists know how to do today is shut up and calculate, because they don't know how it works. It's weird science that's counterintuitive. And that's not true. If you look at it from a virtual reality perspective, you can just look at the logic of the problem and say, there's the answer. No calculations necessary. Well, all the other sciences are like that. You look at the logic of the problem and the logic tells you, what the answer has to be. Quantum mechanics is the only weird science we have. The perspective is wrong. That's what makes it weird. So that's just a little introduction. Now, one of the, I want to start with making a little bit of a connection to what we heard yesterday. And so I have this model, and the model is logical, and it's got all the somehows taken out of it. And it's about consciousness, and it explains remote viewing, of course, and what it is, why it works, how it works, what its limitations are, why those limitations exist. It will explain a lot of the things we heard yesterday. Matter of fact, it was real satisfying to me that after Marty spoke and after Lynn spoke, everything they said, with one minor exception, was perfectly in line with my big toe. My big toe would say, yes, that's the way it has to work. It couldn't work any other way. So when Lynn told us about when you go into your office building and you see the mess and you have to clean it up, if you just say, clean up mess, well, you can maybe make that happen in your mind, but it doesn't do any good. It doesn't work. You have to do the work. Well, my theory says it has to be that way. If you don't do the work, you're not going to get there. Doing the work is where you engage with the problem with your intent at the being level. And when you say, go away, mess, that's an intellectual process that carries no significance. And that turns out to be a logical necessity that it carry significance. You have to be connected there. And so on with all the things they said. The only thing I heard yesterday that was a bit of a clash was the parts when Marty talked about science. Everything Marty said from his own experience was dead on. Everything Will said from his experience was dead on. All the stuff I heard from Jeffrey, yes, I can explain those things and why they're like that. Somebody asked Jeffrey, well, do you know how it is that this guy had these powers? And he said, well, he said that he got them from another dimension, whatever. That's a pretty accurate answer. My theory would support that. But you have to understand, that's a metaphor. When you communicate in, telepathy, if you will, when you communicate with things not physical, the language is metaphorical. Symbols. See? It's always in terms of symbols and metaphors. So if you don't take that answer as a at face value, but you look at what it's actually saying in a metaphorical sense, it's probably the right answer. That's exactly what happens. But we tend to take it literally. And then when you take it literally, you're kind of lost. Well, what does that mean? I got these powers from people in another dimension. But it actually isn't that wild at all if you get the right interpretation of it from a metaphorical sense. So anyway, all this stuff worked really well. Like I say, the Marty's stuff that didn't work was when he was quoting other people, when he was talking about science. You see, we talk about the microtubules and quantum physics that somehow creates consciousness. That's the material world creating consciousness. It doesn't work that way. The material world doesn't create consciousness. It works the other way. Consciousness generates the material world. Consciousness is fundamental. This universe we're in, this physical universe, is not fundamental. It's computed. And it's computed by consciousness. And I'll tell you a little more about the details here as we go on. And then we were talking about or Marty talked about the 0 point field. Has several names. That we're out in outer space. It's not really empty. It's got all this energy, and if you add all that energy up, it's amazing. It's huge. It really doesn't work that way. In a virtual reality, you only compute when there is a player who needs data. Virtual realities don't just compute because it's fun to compute. They compute when somebody requires data. So all that stuff out there that adds up to huge energy doesn't. That's only if you have an assumption of a material reality. Once you assume a material reality, then you end up with those kinds of things. You end up with weird physics. You end up with microtubules that somehow create consciousness. So those are the only parts I heard yesterday that were in conflict. But again, remember, this is just a model. And I am very big on not believing anything. I'm very big on skepticism. And I would entreat all of you, don't believe anything I tell you. If you believe it, that won't help you. Understand it, experiment with it, and make it your own experience. That then you can believe, because it's your experience. It's like Dean Radin. He knows now that bending spoons is a real thing, real magic, as he says. He knows that. He may not talk about it in public, but he knows it. And when you have an experience, you know it. So I don't want anybody to believe, because believing is really useless. You can't grow anything anywhere from believing. You don't gain anything by believing it. So I just hope that you would maybe think about it and test it. Experiment with it. And then believe the results you get, whatever they are, pro or con, and let them lead you to the next step. So always be skeptical of everything you hear. That's important. Another kind of a saying I have is that you need to be open-minded and skeptical. Those two have to go together. And that is actually the only way that you can make progress toward the truth, is if you're both open-minded and skeptical. Because if you have a belief, that belief locks you in. Once you have a belief, then you discard anything that's contrary to your belief. Oh, that's anomalous data. Oh, that person doesn't know what they're talking about. Oh, that couldn't be true, because you have a belief. That's the problem we have with science. Science has a belief, and their belief is in materialism. So when we offer them things like remote viewing, they blow it off because it's contrary to their belief. Belief is a trap. Stay away from belief. Really what I'm going to talk about today is not retrocausality, which was what was I was billed as talking on that subject, but really it's about precognition. And Marty made a good point about precognition and retrocausality kind of going together, and within the remote viewing that you do, they do. Indeed, one is the opposite side of the coin of the other. But that's not always the case. Fact is that there is no such thing as retrocausality. It doesn't exist. This is a virtual reality. Virtual realities are run with a time loop. Time loop always moves on. Okay. There's a couple of basic concepts to understand, and what they kind of philosophy, you might say, and that is, if you talk about consciousness, consciousness makes choices. That's what it does. It makes choices. If you make choices, you need time, because you have a before and an after the choice, right? Choice doesn't mean anything if there's no time. Okay. So consciousness has to have time, and a choice doesn't mean anything if you don't have free will. Time, conscious, free will, they're all logically necessary for each other. On the other side of this philosophical viewpoint, you have materialism. And if you're a materialist, you have to also be a determinist. You can't have materialism without determinism. You can't have determinism without materialism. Those two logically have to go together. And when you have materialism and determinism, you can't have free will. You can't have time. That's why we hear, oh, there's no time. Time is an illusion. You see, the past, present, future are all together, and it's all an illusion. It's just these little slices of time go by, and it makes an illusion for us. That's part of the materialistic, deterministic philosophy set. And consciousness has to be an illusion. Okay? So you see, if you have consciousness, time, and free will, then materialism and determinism is an illusion. See how those two sets are just totally incompatible? So you can't have free will and consciousness and still have microtubules creating consciousness, because that's materialism, that's determinism. Those two are logically don't connect. One denies the other. Okay, so there's a problem there. Okay, so there is no retrocausality, but there is precognition. Precognition is part of the system. We indeed can know the future, but we can only know it in terms of probability, because otherwise it would be determinism. If we could just know it, that future's fixed and we can know it, that's determinism. Well, if that's determinism, then there is no consciousness, there is no time, and there is no free will, you see. So again, we have to keep our philosophy straight. So you only can get information about the probable future, not the future. Now, sometimes that probability is 1. Well, then you might say, well, that's absolute, that's an absolute future, but most of the time it's not 1. Probability of 1 means that it will be this way. The future is fixed then, the probability of 1 that it will be that way. That's a rare circumstance. Probably doesn't even happen in the real world, but sometimes it's close. 0.99999, yes, that happens off and on. That's not all that uncommon. But that's a key idea. We can only know the probable future. Okay, we've already done who I am and where I came from. What I learned from being at Monroe Laboratory, when he turned into that name, what I learned with Bob all those years, 2 things that were fundamental. One is that consciousness is an information system. Now, that's not that hard to understand. We think, what is consciousness? What's information, right? I mean, remote viewers ought to get that better than anybody. It's information. Your consciousness is getting data. It's getting information. Well, if we think about it here, it's just sense data. You can hear, you can see, you can smell, you can feel. You can feel the chair you're sitting in. You can see, you can hear me talking. You have all of that. It's all just data. It's information. So it's not too hard to see consciousness as information. And then the larger conscious system is an information system. Well, information system sounds like a computer, doesn't it? Well, they're related. It's an information system. So that's the first thing I learned, that consciousness is information from my research in the non-physical. Second is that consciousness is fundamental. It's the root cause of everything else. Everything else goes back to consciousness. Consciousness is the source for everything else. Now, if you take those two together, the consciousness is an information system and the consciousness is fundamental, you end up with our reality, our physical universe, then has to be virtual. It has to be computed. It has to be simulated. All right. So the physical universe is a product of consciousness. That was my conclusion when I wrote this book about consciousness. That was 2002 when I published it. At that time, there was maybe 3 or 4 people on the planet that I knew of that thought virtual reality was a really good idea, was logical. Everybody else thought it was ridiculous. Most people still think it's ridiculous. But I'm talking about the scientists, the people there were 3 people that I found that didn't think it was ridiculous, and they agreed with my thesis. And one of them was Nick Bostrom. He's now a professor at Oxford. And the next one was Dr. Edward Fredkin. He was at MIT, very high-powered, well-thought-of physicist from MIT. I think he went to Boston and then to Carnegie Mellon. Does a lot of work in cellular automata, a very bright person. And actually in the middle 1990s, he wrote a paper, presented at physics and computing forums that this indeed was a virtual reality. And he showed his proof, and everybody saw the proof just like they saw the weird double slit and said, oh, that's strange, let's go on and do something else we understand. So there were those, and the last one was John Archibald Wheeler, Princeton. Now Wheeler is a really big gun in physics. Wheeler was around when quantum mechanics was birthed. He was part of the thinking machine that created quantum mechanics. He just died in early, like 2001 or 2 or 3, I don't know. It was in the first half of the 2000s is when he passed on. But he was a very highly regarded physicist, maybe the highest. If you had to make a hierarchy of who was on top of that heap, John Archibald Wheeler had been a good candidate for being on top of the physics world. Well, he invented a lot of things in physics. Black holes, that was Wheeler. That was Wheeler's word, his concept. But the one I like most, and there's several others like that, he's been at kind of the head of a lot of the major discoveries in physics. Well, he made a quote. He says, well, when I started out life, and that was in the beginning with quantum mechanics as a physicist, he said, I thought everything was particles. And then I realized from the quantum mechanics experience, double slit experience, that couldn't be true. Then I thought everything was fields. And now, he says, I know that everything is information. He coined the phrase, it from bit. You've probably heard that. It gets bandied around. It from bit, that means it, everything, the universe, from bits, from information. So, it from bit is a John Wheeler. So, okay, there are only 3 people that agree with me, but 2 of them were physicists, and 1 of them was at the top of the pile in physicists. Yeah, Feynman, the guy who said shut up and calculate, was a student of John Wheeler's. It's one of his graduate students. And so was several other of the top physicists. So he not only was at the top of the list in his physics, but some of the best physicists that came after were his students. And if you ask Feynman, something that Feynman wrote, they asked him about, well, what did you think of your major professor Wheeler? And Feynman said, he was crazy. Well, he was crazy in the sense that he could think out of the box. That's why he was so successful as a physicist. He wasn't trapped with belief. He could think out of the box. And he was vindicated in that just about a year ago with an experiment that verified one of his Gedanken experiments in quantum mechanics that would show that this was a virtual reality. And finally they were able to do the experiment, and it worked just like Wheeler said it would. So that was he wasn't around anymore, but he got a big gold star for that one. Okay, so let's get to the details then a little more. Right now, virtual reality is the biggest new idea in science. It's not just the 3 of us anymore. Over that decade, from 2004 to today, we've gone from virtual reality is way out on the fringe. Everybody thinks it's a nutty idea, except a couple of people. Now, every major physics department anywhere in the world has a cadre of people in it that think virtual reality is not only a good idea, but the answer. And there's a reason for that. The reason is that they're experiments. As time goes on, we can do more and more sophisticated experiments, and the experiments have driven them to that conclusion. The experiments leave them no way out. Physicists don't like the idea of virtual reality. It just brings up a lot of stuff that they don't want to see. If it's a virtual reality, it's computed. Oh, in what computer? Who's the programmer? You see, it brings up a lot of things that science and physicists don't want to deal with because it's not material, it's not deterministic. So they don't like it. They've been, it's been 100 years almost since the double slit experiment that showed that this is not a materialistic reality was done. 100 years later, physics for the most part is still in denial. That's where belief will get you. So it used to be just this one little set of experiments, but then there was more and more and more, and now every day somebody's sending me a paper, some other experiment, some other journal of physics where the people are saying it's got to be a virtual reality. It's the only thing that answers the data. It's the only thing that makes sense. It's called in physics the simulation hypothesis. That is, that our physical reality is a simulation. That's what virtual reality means. What does that mean? If this is a simulation, that means our bodies are avatars. Just like the elf in World of Warcraft, just like your Sims character, avatars. Well, that doesn't accept your brain. Your brain's a physical thing. It's a virtual brain and a virtual body and a virtual podium and a virtual hotel. It's all virtual. You think, wow, that's some good computing there. But yes, it is. But it's not nearly as hard as you think. It's a mistake to identify yourself as your body. You're not your body. You are consciousness. Okay? Your body is the avatar. You, your consciousness, are the player. And this game has a purpose. Okay? The Buddha understood this about 2,500 years ago. The Buddha said this reality is an illusion. And a lot of mystics have said similar things over the time. If you look at some of the indigenous cultures, they'll say that this is the dream. And when you die here, you wake up. It's the same sort of thing, talking about virtual reality. So that's been a topic that's kind of been understood in the mystical world, in the theological world, for a long, long time. But it's not a favorite place of science to go. Okay, let's get on here. This is the way the world works. Now, you see that on the, I went back one, sorry. All right, so here we are here. This is the physical universe. I got two sides now, I have to do this. There's a physical universe that's inside the blue box, right? That's a whole physical universe. And inside this physical universe, that's our physical universe, we have a rule set that's been created to create this Lord of the Rings virtual reality game. And there's such a game. You can go buy this game and play Lord of the Rings virtual reality game. And that game has memory, a game map, results of other players' choices is what the computer does. And this is a physical computer. Right, it's part of what we call physical. I'm saying physical, and I mean that's what we think physical is. And it's creating this virtual reality of this elf, Legolas. And you are the player. You're going to play in this virtual reality game, you see? Here you are down here. This is the player. That's the computer. All of this is physical reality, and here's the game that gets played. Okay, now is Legolas in this game real? No, Legolas in this game is virtual. He's a virtual character. He's an avatar. You are Legolas's consciousness. Legolas doesn't do a thing unless you give him instructions. If you don't tell him to do something, he stands there and does this. He wobbles. Because that's what's boring, is just standing there and not moving. At least wobbling makes him more animated. So that's all he'll do. You have to tell him what to do. Dance, run, fight, whatever. Or he just does nothing. So you make all the choices. The avatar executes them, and then the computer looks at all the players and computes all the players. What are the consequences of all the decisions that all the consciousness made, all the players made in this game? Computer does that, and it sends it out to all the players and says, okay, here's a new state of the game. This is the way it is now. That guy just swung a sword at you, and you're dead now, or whatever the consequences are. Now you, the player, have to deal with that. You have to do whatever you have to do to maybe go heal someplace, or maybe you get your bigger sword out, or whatever you do. Okay, that's the way this game works. There's two things here that you have to kind of realize, and that's these two down here. Okay, now, one of those says that both the consciousness player and the physical computer must exist outside of the virtual reality. Okay, that means they have to be non-physical from the virtual reality's perspective. What that means is if you're Legolas in that computer and you want to find the computer that's computing your game, you're not going to be able to open a door inside of that virtual reality and say, oh, there's the computer that's computing my game. The computer can't be inside the virtual reality. It has to be outside the virtual reality. See? That's pretty simple, isn't it? On the other hand, the player also has to be outside the virtual reality. Legolas is never going to open a door inside his virtual reality and say, oh, there's my consciousness, there's my player playing in here. The player has to also be outside of the virtual reality. When you're outside of the virtual reality, from Legolas's viewpoint, you're non-physical. Because from his viewpoint, his World of the Rings map is what's physical. As he runs around in the World of the Rings map, he runs into a tree, he bounces off and gets hurt. He can get winded, he gets underwater, he can drown, all those things can happen to him. That's his physical world. The consciousness and the computer are non-physical. Okay. We are the same. These are just fundamental logical properties of a virtual reality. All virtual realities have these properties. Here we are. All right. That's you guys sitting out here on your desks looking at me. Except most of us aren't as well dressed as those people. But other than that, you can pretend that these are us, okay, in virtual reality. All right, now if you look at that, the big blue box is what I call the larger consciousness system. Sometimes abbreviated LCS, larger consciousness system. All the rest of it looks about the same because it works just the same. Okay, so here's the computer, but now this computer is a part of consciousness. This player is a piece of consciousness. Well, that would make sense because both the player and the computer have to be outside the virtual reality. What's outside the virtual reality has to be non-physical to us inside the virtual reality from our viewpoint. Well, the consciousness player and the consciousness computer, remember this consciousness system is an information system. Okay, so a subset of that information system is our consciousness. I call that a IUOC, individuated unit of consciousness. And what this individuated unit of consciousness does is it logs onto this game. When it logs onto the game, it takes a piece of itself, a piece of consciousness, and that piece that it takes has no intellectual component. It's just the core being level. And when I say being level, it's similar but not the same as what you call the subconscious. It takes the being level. The being level is the core of your consciousness. It's who you are at the core. The intellect is mostly who you think you are or who you'd like to think. It's your image, it's your self-image. It's not really who you are most of the time. What's deeper is who you really are. So it takes just that part of the consciousness from that individual unit of consciousness, and that free will awareness unit logs on in a total immersive experience. Now when we play World of Warcraft, it's not immersive. We put the game on hold, we go make a sandwich, go to the bathroom, we come back and we start it up again. Immersive means you're in it. Now we get immersive sometimes with things, and people, probably mostly kids, get immersive in their games to where nothing else is going on in the world around them except in the game. And most of us get that way when we read books. If you read a good book that's really grabs your attention, you forget about the chair you're sitting in, you forget about the house you're sitting in. It's just your consciousness and what's happening in that book. You let go of all the rest of your reality. That's immersive. But this is totally immersive experience. So if you have a totally immersive experience, you begin to identify with that avatar as being you, because it's completely immersive. There's no other you to get up and go make a sandwich or go to the bathroom and come back. You are totally immersed. Your perspective is the perspective of the virtual reality that you're immersed in. So you think you are the avatar. Seems that way, because nothing else is in your reality but the avatar. Now, the other thing that I haven't talked about yet is that there's a rule set. It's up there in the corner. It says rule set. It says rule set somewhere up here. Yeah, up there. Rule set. That's what defines the virtual reality. Virtual reality has to be defined by something. That determines all of the constraints that define the virtual reality. Like in the World of Warcraft, your elf can't fly. And I suspect Legolas on that virtual reality game can't fly either. He might be able to flap his arms, but he will never take off because the rule set doesn't support it. If Legolas falls in the lake and can't swim, he'll drown because that's what the rule set says will happen if he keeps his head underwater too long. That's the rule set. Okay, it defines all the play. Now in our virtual reality games, we try to mimic our own rule set because it makes them seem more authentic, more real. What about our rule set? What's our rule set? Well, we have dug out a lot of nuggets of our rule set. It's called science. All the biology, all the chemistry, all the physics are little pieces of understanding of our rule set. That's how the world works. Okay? So now how did we get here then? I'll maybe make an excursion. I shouldn't, but we'll see. All right. You see, I don't pay much attention to my notes. I have them here for comfort whenever I don't really do anything with them. Okay, so how do we end up like this? Talking about the programmer. Who's the programmer? There is no programmer. We have consciousness, this larger consciousness system. And if you're an information system, the one thing that makes or breaks you, the one thing that's important to you is information. Entropy. Entropy is a measure of disorder. It's a measure of disorder. A lot of entropy, a lot of disorder. Well, think of information systems. If your information system has a lot of bits, but the bits are all random, that's maximum entropy, maximum disorder. Every bit's just random. Lots and lots of ones and zeros floating around, but none of them mean anything or connected to each other. They're all random. High entropy. No information. There's no information in randomness. Now you take those bits and you start to order them. Order them in some way that it means something to you, has some significance, some metaphor, some symbol, whatever. You know, just a pretty little pattern like 1, 0, 1, 0, 1, 0. Well, that's something. And it's got information. Because if I say 1, 0, 1, 0, 1, what's the next number? 0, right? That's part of the sequence. That means that series contains information. So order is low entropy. Ordering things. Organizing, that lowers entropy. Ordering. Randomness raises entropy. If you're an information system, if your entropy goes up, you're de-evolving, and if it goes up to the point of everything's random, you're dead. You're not an information system anymore. You're just a potential to become an information system, you see? So now if you're an information system, you've got the same life and death issue that everybody else has. You evolve to more order, to more construction, to more cooperation, to more organization. Now that's positive evolution. And if you de-evolve, negative evolution, if you will, you can move back toward randomness. De-evolve too much, you die. You disappear. You've got to start all over if you can. So this information system has a purpose. Its purpose is to lower its entropy, to survive, to grow, to become. Now, to do that, it has to order things. So at first, there's just patterns. It makes patterns out of its bits. Maybe it's just amused by the patterns, or maybe they think they're cute, or maybe they like the idea of ones and zeros in different configurations, but whatever, it makes patterns. And then when it gets more sophisticated, evolves more, it makes patterns of patterns. And then patterns of patterns of patterns, until it can get things that are really very complex, that mean something to this consciousness. They can have patterns interacting with patterns. This pattern and that pattern go together to make a new pattern. See? And it can do math with all those ones and zeros. It can count ones and zeros. Okay? So this is our larger conscious system, an information system that needs to lower its entropy, needs to evolve. And it has to do that with constantly more organization. Well, eventually you run out of patterns and patterns of patterns. You need something more than that. And when the system gets there, like any other evolution, it's just evolving, right? Things just evolving. It's not that something is moving pieces around on a chessboard to make it do things. It's just evolution. Evolution says whatever can happen does happen occasionally. And when it does, if it's really good and creates less entropy, it persists. If it creates more entropy, it self-destructs. You know, we have the same issue in our virtual reality here in our biology, except our criteria aren't usually stated as entropy, though that's really what it is. Our criteria are usually stated as survival and procreation. Stuff happens, and things develop, and if they help you procreate and help you survive, well, then they continue. If they don't, they go away. That's how evolution works. Well, this system is the same thing. This is not this is a natural system, not a supernatural system, just a natural system. Started from a tiny little cell, it's evolving. The next big technology it evolves, again through trial and error, is time. Time was a good big breakthrough because now it could just go 1, 0, 1, 0, 1, 0, just flip those states and it's got a metronome. Now it can have sequences of patterns. See, a whole new range of things that can be organized. Now there's another skillion ways that you can put things together because you've got time. Now that's called regular time. Before that it had irregular time. There was still change. Without change there's no evolution. Without change there's no choice. Without change there's no free will because there's no choices to be free about. So it still had a time, but it was like primordial time. It was not regular time. It creates regular time. Now you can have sequences. Then when it got to the end of working that technology, it needed something else to give it more opportunities to organize. And what it did was the same thing our biology did. This is just the natural lowering of entropy. Actually, in our biology, the survival and procreation can be explained or described just in terms of entropy, just like this. Entropy is measured with respect to a system. It's system entropy. In our physical virtual reality, if you survive, that is a lower entropy thing. If you can procreate better, that's a lower, it's more organization, more connections, more things you can do. If you de-evolve, okay, then that means you, in that sense, you don't survive. It's not good stuff. It raises the entropy, therefore it's not as effective, therefore it goes away. So evolution in general moves toward lower entropy. Just the nature of evolution. I hope I'm not giving you all a headache. I'm just kind of hammering this stuff in, but anyhow, I tend to be good at giving people headaches. Isn't that right, Marla? Okay, so anyhow, that's the system we've got, right? And this new technology, if you will, was to split itself apart into individuated units of consciousness instead of this one big monolithic consciousness, and let those individuated units interact with each other with free will. Now the possibilities just skyrocket because free will is something that nobody can count on. And all those interactions then are unique, as is all the individuals become unique because every experience that this one has makes it some different than that one. And these experiences all lead to unique individuals, all interacting with other unique individuals, which creates unique synergy and unique stress, and everything is new. Lots and lots of more choices, bigger and bigger decision space, opportunities for organization and cooperation that you didn't have before. So that's what we are fundamentally. Okay? We are these individuated units of consciousness. And we exist so that the system can lower its entropy, survive, if you will, grow, become more, lowering its entropy. That's our job. Now, there's an interesting thing about this, which will answer the question that several people had, both Marty and Lynn, talked about love. Love, somehow, is connected to all this. You know, remote viewing works better if there's this content of love involved in it rather than this content of greed or something in it. If you can get rid of the self-centered aspect of it, let the ego go, it works better. Well, the reason that is look at these individuated units of consciousness. They form a social system, right? They're all interacting with each other with free will. That's a social system. If you look at a social system of interacting consciousnesses, two things logically fall out of that. If they cooperate and share and work together, they can organize and create something much more than if they don't cooperate, if they don't share, if they fight with each other, they tear each other down. Okay? That tends to disassemble, that tends to destroy, that makes the system higher entropy. Well, those two opposite poles are love and fear. So you have these ideas of love and fear. So the ones that are lowering entropy and forwarding the larger consciousness system's evolution, those are the ones that are growing toward love. And how do they do that? They do that by making choices. Their consciousness, that's what consciousness does, it makes choices. They get to make choices. And every time they make a choice, that choice can be because of an intention of love or caring or cooperation or any of those positive values, or it could be because of fear. You see, fear is not hate's not the opposite of love. Fear is the opposite of love. Fear reduces trust. Without trust, interactions become difficult. They certainly don't build very well. With fear, it's all self-centered. With fear, it's I got mine, and I want yours too. And I'm going to make sure I keep it, and you feel the same way. And that doesn't build. That doesn't cooperate. It doesn't make things better. So that pulls you the opposite ways. Fear self-destructs. So that's where the love connection comes from. That's where our purpose comes from. Our purpose now is to grow up and become love, to lower our entropy because we're part of the larger system. We are it. You know that old saying, is it, we're all one? It's true. We're all part of one larger consciousness system. That's the source, and we're a piece of it. And our job is to make decisions that move us toward lower entropy. I call that higher quality consciousness. You might call it spiritual growth. It's all the same sort of thing. Okay? So that's our job. That's why we're here. And the reason that a virtual reality needs to be made, so why the virtual reality? Why does that come from? Why is that necessary? Well, think about all these individual units of consciousnesses. They are making choices. They're evolving or de-evolving. As they evolve and de-evolve, the system evolves or de-evolves because they are the system. And it's like a chat room. You're like in a chat room with 100,000 people in a chat room. No rules, just a big chat room, because that's what consciousness do. They trade information, they communicate. Well, that's going to be a hard place to learn to grow up and make good choices because there's almost no consequences, no feedback. Everybody's an island to themselves. Where's the stuff where's the traction, in that? You need an environment in which there's consequences and where you get feedback immediately from the quality of your choice. That's a schoolhouse that will teach you, not one that doesn't matter what you do anyway because you're an island. It's just you in the chat room. You can say anything to anybody for any reason. Doesn't have to be true. There's no value in being helpful. There's not really much value in anything. So the system says, we're evolving along at a very slow rate. We could do better if we had a virtual reality. Now, they already were in a virtual reality in the sense that the first virtual reality was when the system created the individual units of consciousness and created a rule set that defined how to communicate. So just the ability of these things to communicate with each other puts them in a virtual reality. It's a rule set that defines your communication. But now we need another virtual reality that has a lot tighter rules. How do we get that? Well, this thing evolves. There's not a programmer. What happens is it tries to put together a rule set that would create such a virtual reality. Well, it makes up some rules, runs it. It's a computer. It's an information system. It can compute as well. It computes the logical results of those rules. And after a while, a million years go by and it fizzles out, blows up. It's unstable. Not long enough. So it fiddles with the rule set, does it again. Maybe goes a little longer, and so on. It just evolves. Ever wonder why when the physicists talk about the Anthropic Principle, about we have all these numbers that that define our universe, that if any one of them was modified even in its the last decimal place, like the 10th decimal place, the whole universe would fall apart? I don't know if you've read those, but that's a fact in science. There's several of these, like 6 or 7 of these constants that would just change everything if even the tiniest little piece of it was changed. It's called the Anthropic Principle. You can Google that. Well, that's why, because this thing evolved. It kept getting modified and modified to make it better and better, and these numbers got more and more precise. Oh, I see, this is what caused it to blow up. Well, let's just add another digit to the end of that to make that force a little stronger. See if that doesn't fix it, you see. And so on, we do that. All right, so that's why the Anthropic Principle is the way it is. Yes, this reality was designed for us. It is an intelligent design. We're consciousness. We're pieces of this larger consciousness system. We can think. We can make choices. We can plan. Do we think it can't? It somehow is dumber than we are? I don't think so. It can think. It can plan. It can organize. It can make virtual realities. If we can, we're a subset of it. It's got more than we do. You see, so whatever we can do, it can do better. So it's the superset. We're a subset. Okay, so now we've got what our purpose is. Why is there a virtual reality? So that we can get into this tighter rule set where our choices matter more. And this is the virtual reality we live in. That's why we have this physical universe. That's why we have all these bodies that are avatars, and we as free will awareness units are totally immersed in making the choices for that avatar. And we have to abide by the rule set, which is the thing that evolved it. Okay? So where does it all come from? You've heard that our universe comes from the Big Bang. I would suggest it comes from the Big Digital Bang. That's when the system pushed the run button and it started the simulation with that rule set, started evolving. And as it evolved, it started with some initial conditions. Initial conditions was a plasma, very small point, very high pressure, very high temperature. Then that's initial conditions in the simulation. Then the run buttons hit and big digital bang. Because of the rule set, it expands, it cools, suns, planets, everything. Eventually you end up with the sun of ours, Earth, biology, all this stuff evolves then. And somewhere along that line, the avatars are interesting enough for consciousness players to log on and play their free will choices. Every individuated unit of consciousness, it's a player, every avatar has a certain decision space. It's another term of mine. These are the choices that they have. And the free will is not the same free will that a lot of people talk about. Sometimes when people say free will, they think that that's, if I have to do something I don't want to, then I obviously don't have free will. Free will doesn't mean you get everything you want. It doesn't mean you have a genie with unlimited wishes. That's not free will. Free will says that I've got these decisions that I know I've got, even though there may be a whole lot more that you don't know. Choices, choices that you can make, a decision you can make. So let's say for numbers that I know that in this situation I've got 10 choices. Maybe there's really 50 choices, but I only know 10. My free will allows me to pick one of those 10 as to what I'm going to do in that situation. How am I going to feel in that situation? See, that's free will. That's decision space. So a dog has decision space. A bumblebee has decision space. A little tiny decision space. Not a whole lot of decisions they make. Humans have a lot of decision space. How much decision space does a dolphin have? Or an orca? Everything that has a decision space that is finite, that means not zero, is conscious. Everything that has a zero decision space is not conscious. How many decisions does a rock make in a day? They can't decide to roll downhill or not roll downhill. That's just the algorithm. Just is the way it is. A lot of randomness in it, yes. But that's just the way it is. We make choices. We have free will. We're conscious. So that's kind of a dividing line between what is conscious, what does it mean to be conscious, what's conscious and what's not. Decision space that's finite makes choices. One that isn't, if it has zero choices, then you don't qualify as conscious. Again, this is my model, so don't believe it. Just listen and see if it makes any sense to you. Okay, this is a funny looking curve, and I only want to make one point here. This is the mechanism that is the basic algorithm, you say, or the basic method that's used to run this virtual reality. What we have in this chart is 26 possibilities in our decision space. I got one for each letter of the alphabet. So A through Z, there's 26 of those. So I got a choice. A situation's come up, and there's 26 different things I might do. Right? These are my choices. All right. Out of these 26 things, you see, if I do thing A, if that's the choice I make, then there's just one A there. In choice B, there's two B's there, two C's, one D, zero E's, one F, and it goes on up. And by the time we get to K's at the peak, you see there's 25 K's. I don't know if you can actually tell that's a K or not, but there's 25 K's piled on each other there, and so on down through all the letters. So you see some things are more probable than the other. Now, the way you determine what happens here is by taking a random draw from the probability distribution of the possibilities. These are the possibilities, 26 possibilities. Now, if I add up all the letters that are in there, if I add up the 1A, the 2Bs, the 25 Ks, I add them all up, I get 163. So I'm going to take all 163 of those letters and I'm going to put them in a box. So a box, think of a box with 163 pieces of paper in it. Each piece of paper has a letter on it. 25 of those pieces of paper say K. One of them says A, and so on. I'm going to shake the box just like in the raffle business. I'm going to reach in and I'm going to make a random draw out of that box, and I get maybe an H. That is the choice. Okay, that's the thing. That's the possibility. Now here's how that gets applied. When you're in a virtual reality, uncertainty is a very key element. It's a very key element in quantum mechanics as well, and you'll see it all works the same way. There's a lot of uncertainty. Where you have uncertainty, you also have more possibilities. Uncertainty creates possibilities. If there's only two possibilities, well, then there's not a lot of uncertainty. It's either A or it's B, two possibilities. If there can be 26, now there's a lot more. There's more uncertainty as to what you're going to get there when you make a measurement. These are the results of making a measurement. I probably didn't make that clear. These are the results of making a measurement. Making a measurement means you do something. You open your refrigerator door. You look in your telescope. You do something that causes the system to have to give you data. Making a measurement in World of Warcraft means you pull out your sword, or you swing it, or you make some other kind of choice, and that creates something, and that's your measurement. So these are all the possibilities. And for example, in a virtual reality, if you're an astronomer and you have a brand new telescope that looks further than any telescope that's ever been made, right? It goes a lot further out in space, and you look into a sector of space, you're going to see something nobody's seen before. What do you think you're going to see? Well, there are, say, 10,000 possibilities of what could be there. Now, those possibilities aren't just random. They have to connect with what we know is already around it. We're not going to look in outer space and find, dancing pink elephants and tutus, or, palm trees, growing on suns and things. You're not going to find that because that doesn't work for us. So it has to fit in with everything we already know. That's a constraint. So within those constraints of what we already know, say there's 1,000 different things it could be. Well, you'll have some kind of distribution like that. The scientist looks in his telescope, takes his picture, and when he takes his picture, somebody takes a random draw from those 1,000 possibilities, and that's what he sees. You see? Now we could take another one, we could make it more land-based, and we could say you walk in some place on the earth that nobody's ever been, and you go into this virgin woods. Let's say it's in temperate climate zone, and you're not going to have probably the birch trees that you would have at a higher altitude. If it's too high an altitude, you're not going to have palm trees. So there's constraints, but within those constraints, there's a whole lot of different ways that it could be. And what you see when you walk in is a random draw from the distribution, probability distribution of the possibilities. That's the way virtual realities work. Okay. Now we can go our first step here into quantum mechanics. In quantum mechanics, there's nothing special about it. Physicists will tell you that quantum mechanics is a special world with its own special physics. And it doesn't work like the macro world. It's a different world with different rules. It's not true. It's the same rules there. When you have a double slit experiment where you're sending single particles toward these two holes in a background, and you want to know where they're going to hit, well, the way you find out is all the possible places they could hit. You take a random draw from that distribution, and that's where you place the particle. That's where it goes. So quantum mechanics works exactly like astronomy or anything else. That's just the way our reality works. It's not a science that's different with different rules. Okay, well, here's a pattern. We're going to look at this a little deeper. Here's a probability pattern. That's the probability pattern that you take the random draw from when you're doing a double slit experiment. So down along the x value are all the different possibilities, and the ordinate is the probability, and all of those possibilities are put in a box. The box is shaken, somebody reaches in, pulls one out, and that's where that particle gets placed on that screen in the x dimension. The y dimension, which is the slit, is irrelevant. So that gets done over here with this kind of probability distribution, which means it's random. Doesn't matter where it is in this y direction. It only matters how it's spread out in the x direction. We'll see that a little later. So that's the kind of distribution you get. Next. All right. Here we'll talk a little bit about double slit. Now, I'm taking these slides from other presentations, so I'm not going to talk about everything on the slides. They're just pulled out of other presentations that I've done. But double slit is, here's the two slits. Here's some kind of a gun that throws particles out one at a time. These are detectors, which you see are off. They're detectors of the slit. They detect whether or not a particle has gone through that slit. Okay, this throws out particles. The particles, when they get thrown out, are such that they have an equal probability of landing, you know, on one slit or the other, or in between the slits or someplace else. You know, all that's done in probability, but we can just, to simplify our problem, let's just say when it gets fired, it has an equal probability of going through either slit. Okay, if it goes through a certain slit, we could turn that detector on and say, particle just went through the slit. But these are all turned off, which means there is no which way data, which is which slit did it go through data. And what happens then is here's this diffraction pattern that you get. The reason it's tall is because these slits are tall, and that's the y direction, and that's random. This is the x direction we just talked about, and as you see, these patterns here are made up of dots. This one in the middle is darker. Can I show you over here? The one in the middle I'm talking about is darker because there's more dots in it. Well, there's more dots in it because there's a higher probability here of getting that x value. You see? So now the next one is a little less dark because this peak is a little less high, and the next one's less high and less high. So they get less dark as you go. So all these are full of dots. The middle one has the highest density of dots, and the last one that has a low density of dots because that's that little peak. So it's the little peak out here on the end, this line out here on the end with all those dots in it. Now, I don't know if you can't see individual dots, I suspect, from sitting where you are, but you can kind of see it's fuzzy and made of particles. So that's how that works. So if there is no which way data, which slit did it go through, then these particles go through one slit or the other and end up distributed on this screen like that, because that is the probability distribution. Okay, and there's a lot of reasons why that is that way. Why does it have to be that distribution, not something else? But that's a longer story than we have time to tell. But that's the way that works. All right, I just wanted to go through that. Let's see what's next. Okay, now here is a case where these are turned on. We have, these are on, so green ON there, if you can read it. So these detectors are turned on, and these recorders are turned on. That's the R1, R2. They record the detections, so you know how many, which particle went through which slit. When that happens, you know what slit it goes through. And if we know it goes through the slit, then all it can do is go straight through here and hit the screen right behind the slit. That's because at this point, that particle became physical. Before that point, the particle was not physical. What makes something physical? Remember the picture of Legolas and then of ourselves? What makes something physical is that we get data in a data stream from a computer showing us something on the screen. That's what makes something physical. If there's a consciousness, a conscious player gets data. He makes a measurement. He says, oh, what's that over there? Well, all the things that are possibly over there, one of them gets random, drawn, and that's what's over there. Now he's going to maybe interact with it or so, but it becomes that thing exists over there because he's got that data in his data stream defining that thing. In your video game, the reason that monster is standing behind that rock is because a monster standing by that rock is put in a data stream that's sent to your computer. Reality is defined in terms of the data stream to the players. Well, that is some interesting concepts around it. That means all of us live in our own private reality. We all live in a different reality. We all see reality as our data stream. That defines our reality. Just like the data stream from our computer defines where Legolas is. That reality and that virtual reality. Okay? Now, the computer doesn't send data unless a consciousness player requests it, needs it, it's logged on. World of Warcraft doesn't just generate lakes and trees and monsters behind rocks when there aren't any players in the game. Only when a player logs on does it send data to that player. Okay. So when it gets to this point where we make a measurement, then that means the system has to provide us some data. What's the result of that measurement? Well, because of the logic of the detectors, whenever a particle goes through one slit, it has to be a particle. That's when the potential particle becomes an actual particle. And once it's an actual particle, it can't do anything except go in a straight line because that's the way actual particles are. As long as it's a potential particle, it doesn't exist in this reality yet. So when we didn't have the detectors on, we had potential particles all the way up to the screen. And then, where do they come? Where do they land? Random draw from the distribution of the probability of the possibilities. That's where it comes from. Okay? So there is no particle until you make a measurement. In physics, that's called the measurement problem. What I've tried to tell you in this, bringing you up, kind of bring you up conceptually to a point where when we start talking about remote viewing and talking about, and we're not very far from that, and talking about looking into the future and so on, you'll have a context for which all that will make sense. Or if I just started with that, it wouldn't make sense. It would just sound like I was babbling nonsense. It may still sound that way to you, but at least I have hope that some of you will find a context here in which this doesn't sound like babbling, but it doesn't make sense. So we will, we've got who we are, what we are, virtual reality, why we're here, why the virtual reality, what our mission is, and we've seen, can I make just one more point with this one? And I'll move off of the slide. Can I finish the slide? All right, here's going to be our first look at retrocausality. This is going to be quantum retrocausality. There's a set of experiments called delayed erasure experiments. And if you Google delayed erasure experiments, you'll find out about them. And what happens is that this experiment, we know, will produce these lines on a screen. It always does because we're collecting this information. Note here, information's key. It's because we collect the information that we get that result. That's why. That's the causal thing. It's the collecting the information that makes it available to us, puts it in the game. Us, we're the consciousness. There's no consciousness here, there is no game. Okay, so we run this experiment. Let's say we run it 10 times. And then we look at the results, and 10 times we get this result on the screen. No surprise. Now let's say we run it another 10 times. And we've got 10 screens with their results on them, but nobody's looked at the results yet. But we got 10 screens, in envelopes or sitting someplace that we just haven't looked at, but we run it 10 times. And we're pretty confident if we look at them, they're going to look like this. And if we did just look at them, they would look like that. But we're not going to just do that. Instead, we're going to take, out of that 10, we're going to randomly select 5 of them, half of them. And the random 5 that we take, we're going to get their detection data, and we're going to burn it. Without looking at it, we're just going to set that envelope on fire. Now the detection data is gone. What's going to happen? And let's say we do that the next day, or the next week. We come back a year later and pick out the 5 and burn the detection data. Well, this stuff's been sitting around then for the year, right, waiting for us to open it up. We burn the data, and when we open up those envelopes, half of them look like that, and the other half have diffraction patterns. Ooh, weird, right? See, physics is a woo-woo too. So that's the weird quantum mechanics, delayed erasure experiment. The delayed erasure means that the erasure takes place after the data has been collected. So you collect the data, then you do the erasure, and it makes a difference what you see here. And it seems like that's retrocausality, because something you did now changing something that was done in the past. Well, in the past done? I mean, when the past is done, then it's supposed to stay that way no matter what you do in the future. It's supposed to, but it doesn't happen. But there really is no retrocausality. It's only an appearance of retrocausality, which is the way all retrocausality is. The fact is, you don't, until somebody looks at that data isn't physical yet. It's still just potential. It's not physical. And don't look at that data until after this data is erased, then it's going to represent the state of when that data doesn't exist. You see? So it's just potential data until some conscious player says, computer, show me what's in this envelope. Then it sends down data. And then you look at the envelope, and now that result is in this physical reality. Before, it was not. It was just potential. Well, you've changed the logic of the situation before you've asked the system to give you an answer. You see, that's how it appears to be retrocausality, but it's not really. If you have the right perspective, you see that it's not retrocausality at all. So I just wanted to finish up the experiment, and then we'll let that go.